Welcome to the Embraer E175 Systems Training Course Fuel module. In this module, we will introduce the fuel system, describe the fuel tanks, talk about fuel quantity measurement and the low-level warning. We'll also talk about the fuel pumps, the fuel crossfeed system, the engine fuel shutoff valve, and refueling and defueling the aircraft. We'll also talk about controls and indications for the fuel system before we talk about the limitations and normal and abnormal procedures associated with the fuel system. The purpose of the fuel system of the Embraer E-jets is to store fuel and provide a continuous supply of fuel to the engines and the APU. Fuel is stored in two integral wing tanks that can be linked via a crossfeed valve. Additional plumbing provides tank venting and allows tank filling as well as ensuring fuel supply to the engines themselves. Overall, the fuel system is quite simple and is designed to operate fully automatically without pilot input under normal conditions. Fuel in the Embraer is stored in an integral tank in each wing. Fuel flows through the tank between the ribs that frame the wing's shape. The ribs help partition the fuel in the tank to prevent fuel from sloshing around, and flapper valves within the wing ribs permit fuel to flow downhill towards the wing root as fuel is consumed. The maximum quantity of fuel within each tank is 4,714 kilograms, or 9,428 kilograms total between both tanks. Within each tank are several specific compartments, a collector tank and a surge tank. The collector tank is the innermost area within the wing tank. It is designed to keep the fuel tank pumps always submerged in fuel, even as the fuel level in the wings overall falls below the level of the pump. 3 jet scavenge pumps located in the main parts of the fuel tank gather fuel from the main tank and move it into the collector tank, ensuring the collector tank remains full even when the rest of the tank has been drained. The surge tank is an extra tank outboard of the main portion of the fuel tanks. It collects fuel that may enter the tank vent system during wing down or other uncoordinated maneuvers. This helps prevent fuel spilling overboard. This fuel can then drain back down into the main tank through flapper valves as fuel in the main tank is used up. A vent system ensures air can enter or leave the fuel tanks as the fuel quantity changes and also as the outside air pressure changes. This prevents structural failure from excess pressure differential between the inside and outside of the tanks. The vent lines run along the top of the tank, linking various tank sections together with the surge tank. The surge tank is then vented from the top to the outside atmosphere through NACA anti-icing vents. The vent lines are sufficient for all normal operations, but an additional high-capacity pressure relief valve is also provided to prevent overpressurization in case of line blockage. 2 water drain valves are mounted at the low points in each tank where water will collect, as the water is heavier than fuel. Each tank is designed to normally feed the engine on its corresponding wing, with the APU being fed from the fuel line in the right tank. Normally, fuel is measured through a series of sensors located throughout the tank that can detect the total mass of the fuel within the tank. This information is transmitted to the ICAS to be displayed as a fuel quantity. The quantity is accurate to within 2% of the indicated value plus 0.75% of the total tank capacity. In case of failure of the electronic quantity measurement system, 3 magnetic level indicators, also known as dripsticks, are mounted within each wing. These can be used while on the ground to determine the level of fuel in the tanks. The indicator is unscrewed and allowed to fall freely until stopped by magnets floating within the tank. The level is then read where the stick protrudes from the wing and translated into a quantity using a table provided in the AOM fuel servicing section. An additional independent low-level sensor is installed in each collector tank. This sensor is independent of the fuel quantity indication system, and when the fuel falls below the level of the sensor, the fuel low-level ICAS warning is triggered for the corresponding tank. Under normal conditions, this sensor is activated when the fuel level in the wing tank is approximately 300 kilograms. Under normal conditions, the scavenge ejector pumps would make sure that all of this remaining 300 kilograms is in the collector bay. However, if some or all of the scavenge ejector pumps are not working due to a malfunction or a lack of return fuel pressure during an engine failure, there will be much more fuel left in the tank outside the collector bay. In this case, the fuel 1-2 low-level warning will trigger with up to 1,800 kilograms still in the tank. If this has occurred, it is possible for the engines to flame out due to a lack of fuel being delivered from the pumps. If the aircraft exceeds a pitch of 15 degrees nose up or down, any uncoordinated maneuvers, or negative Gs. Several different fuel pumps move fuel around the system to maximize system reliability. These include one ejector fuel pump per wing, 3 scavenge ejector pumps per wing, one AC electric fuel pump per wing, and one DC electric fuel pump in the right tank only. The ejector fuel pump is the primary pump that transfers fuel from the collector bay to the engines. An ejector pump is a simple system with no moving parts. The ejector pump is basically a venturi, a small volume of high-pressure fuel that is returned from the engine's high-pressure fuel pumps, passes through the venturi. The high speed of the fuel decreases its pressure, and this lower pressure sucks a larger quantity of fuel from the tank into the venturi and carries this high volume of low-pressure fuel to the engine. This simple design requires no electricity, which ensures a continuous supply of fuel even in the event of electrical failures. 3 more ejector pumps, called scavenge ejector pumps, move fuel around the wing fuel tanks. They function in exactly the same manner as the primary ejector fuel pump and are powered by the same high-pressure fuel being returned from the engine. However, the function of the scavenge ejector pumps is simply to move fuel from low areas in the main parts of the wing tank into the collector bay. These pumps ensure the collector bay is always full of fuel, even as the rest of the tank level drops. This ensures the primary ejector pump and the electric pumps always have fuel, even when the aircraft attitude changes. Each wing also has an AC-powered electric fuel pump. This pump serves as a backup to the primary ejector pump when it is not able to function. This could be due to mechanical failure or simply a lack of fuel pressure due to an engine being off. This pump provides fuel pressure during engine starts, ejector pump failure, or if the APU is running while the engines are off. The left AC pump is powered by AC bus 1, and the right AC pump is powered by the AC essential bus. A DC fuel pump is installed in the right tank only. The DC fuel pump is designed as a further backup in case the ejector fuel pump is not available, for example the engine is off and no AC power is available. The most common time the DC pump runs is to start the APU when no AC power is available and only DC battery power is available. However, the DC pump could also be used to start an engine if an AC pump is not available. However, the DC pump's output is smaller than the AC pump output. The DC pump is powered by DC Essential Bus 2. Normally, the fuel system is separate for each side of the airplane. However, Crossfeed does link the two systems after the ejector fuel pumps and electric fuel pumps. The valve that links the two sides of the system is normally closed, but can be opened to feed both engines from a single tank when necessary to correct a fuel imbalance, especially during single-engine operations. When the crossfeed knob is selected to the low 1 position, the crossfeed valve opens and the AC pump 2 is activated to increase the pressure coming from the right number 2 fuel tank. This will force more fuel from the right tank through the system to both engines. Since the fuel pumps always supply more fuel to the engines than necessary, some of the fuel will be returned by the engine to its respective tank, and the fuel level in the low tank will actually rise very slowly. For example, if engine 1 is being fed from tank 2, the excess fuel from engine 1 is still returned to tank 1, and so tank 1's level will actually rise slightly. Note that an ICAS message, fuel equal crossfeed open, will appear anytime a fuel crossfeed is commenced before the fuel imbalance message is triggered. This message is information only, but serves as an important reminder, as fuel crossfeed can introduce an imbalance beyond limits after only a few minutes if it is not carefully monitored. The engine fuel shutoff valve is located within the wing, in the feed line from the pumps to the engine. This valve is only closed by pulling the engine fire handle. Since the valve is in the wing, when it is closed during an engine fire scenario, no fuel can enter the wing nacelle area at all. Refueling and defueling is normally accomplished through a single pressurized refueling point. The refueling port is located on the refueling panel underneath the leading edge of the right wing. An access panel protects the refuel panel and maintains wing aerodynamics. When the panel is opened, a light illuminates automatically to assist in night and low light operations. Power to control the refueling system can be provided by the DC bus 1 and 2 if the aircraft has AC power available, or the hot battery bus 2 if the aircraft is unpowered. Fueling is controlled by a fuel conditioning unit or FCU. Normally, refueling is conducted in auto mode. In auto mode, personnel pre-select a desired fuel quantity to fill the tanks on the refueling panel. In this mode, the FCU opens the refuel shutoff valves and monitors the fuel quantity throughout fueling. When a tank has reached a level equal to half the total desired fuel, the FCU closes the tank's refuel shutoff valve. This ensures the correct amount of fuel is delivered and balanced equally between both wings. In manual mode, the FCU is bypassed. As long as the refueling switch is open, the refuel shutoff valves also remain open. Personnel must manually move the refueling switch to closed when the desired fuel level is reached to close all the refueling valves. For either mode of pressurized refueling, a high-level shutoff trigger will close the refuel shutoff valves when the fuel in a given tank exceeds the maximum volume. This is indicated by the valves closing and a stop L over or stop R over message appearing on the refueling panel display. Note that it is possible for this high-level shutoff to trigger prior to reaching the nominal tank capacity of 4,714 kilograms. This would usually occur on a warm day when the fuel is less dense, as the high-level shutoff triggers when the tank reaches full volume, regardless of the actual mass of the fuel in the tank. It is not possible to bypass the high-level shutoff through the pressurized refueling. As a backup, the aircraft is also equipped with a single over-wing refueling port on each wing. However, these are seldom used in reality. The aircraft can be defueled, if required, through the same refueling panel. A defuel switch allows fuel from the tanks to exit through the pressure refueling port, and this can be achieved either through suction from the defueling vehicle or with the assistance of pressure from the aircraft's fuel pumps. The refueling system is primarily controlled from the fuel panel on the overhead panel. This panel is laid out in a diagram which basically resembles the layout of the key components of the system. As you will see, the controls are very simple and, under normal operations, are not operated by the pilots, as the system is fully automatic. At the bottom of the panel are two AC pump switches for pump 1 and 2. Normally, these are left in auto mode at all times. The pumps will be activated automatically by the system when needed. This includes during engine starts, anytime pressure from the ejector fuel pumps is insufficient, during APU operation for the right AC pump, and during a crossfeed operation, the source tank pump will operate to boost pressure from the source tank. In off mode, the AC fuel pump will not operate for any reason. In on mode, the AC fuel pump will operate continuously until another switch position is selected or AC power is removed. A DC fuel pump switch in the center of the panel works in much the same way as the AC pump switches. In auto mode, the DC pump will be activated when fuel pressure is required from the right tank and AC power or AC pumps are not available. This is primarily the case for APU starts from batteries. The off position prevents the DC pump from operating for any reason, while the on position forces the DC pump to run continuously. At the top of the panel is the crossfeed selector. Normally it is in the center off position, where the crossfeed valve is closed and no crossfeed operation takes place. The low 1 position is used to provide crossfeeding where tank 1 has a low fuel level. For low 1, the crossfeed valve opens and the right AC pump is activated, assuming it is in automatic mode. This increases pressure output from tank 2, forcing fuel from tank 2 into both engines and ensuring its level drops faster than tank 1. When low 2 is selected, the crossfeed valve again opens, but this time AC pump 1 is activated, reversing the process. The other controls for the fuel system are located on the refueling panel underneath the right wing. The refueling switch controls the position of the refueling valve behind the pressurized refueling port. Open, the port is opened and refueling can commence. Closed, the refueling valve is closed. Above the refueling switch are two lights that indicate the status of the refueling shutoff valves. When the valves are closed, the lights illuminate. Above this is the refueling mode selector, which is normally guarded in auto mode. In auto, the refuel shutoff valves close automatically when the pre-selected fuel level is reached in the tank. In manual mode, the refueling shutoff valves remain open as long as the refueling valve is open, unless the high-level shutoff triggers to close a refuel shutoff valve. The power selection switch allows personnel to select a power source for refueling operations. In normal, guarded mode, the refueling system operates off the aircraft's electrical buses, specifically DC Bus 1 and 2. However, if aircraft power is not available, battery mode can be selected. In this case, all the refueling system runs off battery 2 through the Hot Bat Bus 2. Be sure not to leave the switch in battery mode when refueling is complete to avoid excess drain on the batteries. The defueling switch has two positions. Closed, the defueling valve is closed. Open, the defueling valve is opened, and fuel can move from the tanks back through the refueling port to allow defueling. The defueling light will also illuminate while the valve is open. Finally, the display shows the fuel quantity in the tank on the top line and the pre-selected fuel quantity on the bottom line. Moving the increase-decrease spring-loaded switch will increase or decrease the pre-selected fuel quantity. The other switch on the display is used to control and test the display and is also spring-loaded. Selecting Tank Cell cycles the upper line of the display. When first powered on, the upper line shows the quantity in both fuel tanks, indicated by a T for total. Pressing Tank Cell once displays the left wing fuel quantity with an L. Pressing it again displays the right fuel quantity with an R, and pressing it again will return you back to the total fuel value. Pressing the test position will test the display system to ensure all the display segments are working correctly. It is worth noting an important safety feature of the refueling panel. The guarded switches are in their normal or safe for flight position when the guard is closed, and the design of the access door is such that the door cannot be closed and latched if any of the guards are not in their correct guarded position. As with most systems on the Embraer, the status of the fuel system can be monitored on a dedicated fuel synoptic page on the MFD. The quantity of each tank is indicated on each tank, both numerically and with an arrow on a tank level scale. The scale indicates a normal, white range, an amber caution range, and a red, low fuel range. The color of the digital readout will also change, with green for normal, amber for caution, and red for low fuel. The total fuel quantity for both tanks is displayed at the bottom of the screen, along with a fuel used indication, and the quantity will change colors in line with the tank indications. The fuel used indication reflects the current flight and resets when the first engine is started. Fuel lines are shown linking the various components of the fuel system. The lines display either white if no fuel pressure is present, or green if pressurized fuel is present in the line. This green-white convention also extends to the fuel valve and pump symbols. Note that it is normal for fuel pressure to be low enough to not register and thus be shown as white when engines are still on, but they are running below 60% N2. The status of all the fuel valves in the system is shown on this screen. The engine shutoff valves, the APU shutoff valve, and the crossfeed valve. A valve that shows an inline flow line is open and may be either green or white depending on fuel pressure. A closed valve will show a cross-line flow that will be white. A diagonal flow line indicates a valve that is in transit, neither fully open nor closed, and may be green or white. An amber circle with no flow line at all indicates the position of the valve is unknown. And a valve with a yellow X over it indicates a valve that is open or closed as shown, but its position is not in the commanded position, and it is therefore likely failed in that position permanently. The primary fuel ejector pumps are shown here and are either white or green depending on if the pump is active or not, or may appear amber if the status of the pump is unknown. All the electric pumps are shown using similar conventions. A pump with a green windmill is on, and a gray windmill indicates off. An amber windmill indicates a pump whose status is undetermined, and an amber X over the pump symbol indicates that the pump is not in the commanded setting and is either failed on or off as indicated by the green or gray windmill. The final indication on this screen is a fuel temperature indication. Note the temperature is only measured in the left tank and indicates green for a normal range, amber for a cautionary range, or amber dashes if the information is invalid. Since fuel is obviously one of the most important parameters of operating an airplane, the fuel quantity is also displayed permanently on ICAS below the engine indications. The indication shows each tank level as well as the total fuel level for the aircraft. Similar to the MFD, the values will change color from green, normal, to amber, caution, to red for low fuel level. Above the fuel quantity indications, fuel flow indications in kilograms per hour, or pounds per hour if the aircraft is so configured, are shown for each engine. These are either green or amber dashed if no valid data is available. The primary limitation of the fuel system is the max tank imbalance, which should not exceed 360 kilograms. The temperature limit for fuel is minus 44 degrees Celsius for almost all types of fuel approved for this aircraft, except for Jet A, where the temperature limit is minus 37 degrees Celsius. The final limitation of the fuel system is that the crossfeed selector must be off for takeoff and landing. Under normal operations, no procedures are required for the fuel system. The system operates fully automatically. The only part of the system that may normally be used during flight is the fuel crossfeed system. If a fuel crossfeed is desired, determine the lower tank and select the crossfeed selector appropriately. Monitor the fuel crossfeed carefully, as it only takes a few minutes for the maximum imbalance of 360 kilograms to be fully equalized at most power settings, and it is very easy to overshoot the target if the crew is distracted by other tasks. When the crossfeed is complete, simply move the crossfeed selector back to off. We will now discuss some of the failures associated with the fuel system. As always, follow your company checklist and procedures. There are numerous fuel failures that require no pilot action other than considering the future ramifications of the failure. Crew awareness items include fuel kilogram-pound mismatch, fuel transfer fault, fuel transfer switch not auto, fuel transfer vent fail, and defuel shutoff valve open. If any of the individual fuel pumps fail, they should be switched off to ensure no electricity flows through the failed pump now or later. Sparks from a failed pump in a tank are a very self-explanatory hazard. If fuel feed 1 or 2 fault appears, there is a problem with the amount of fuel moving through the fuel system. If in flight, continue to monitor all the fuel systems. If on the ground, there is a procedure to increase the pressure in the system by accelerating the engine and activating the AC pump to push more fuel through the system. If this does not solve the issue, maintenance action is required. If fuel tank low temp displays, the fuel is cold enough that ice crystals forming in the fuel is a possibility. The checklist requests the pilots to accelerate to increase the total air temperature passing over the wings and hopefully heat the fuel. If this proves insufficient, a descent to warmer air should be commenced as soon as possible. If fuel crossfeed fail displays, ensure the crossfeed selector is off. In case of fuel asymmetry that cannot be rectified, asymmetric thrust might be required. If APU fuel shutoff valve fail appears, do not restart the APU. If engine 1 or 2 fuel shutoff valve fail appears and the fire handle was pulled, then the valve has not closed when commanded. Your best bet is to shut off the associated pump and crossbleed to reduce the fuel flow to that engine as much as possible. If the fuel imbalance message appears in flight, the checklist leads us to evaluate the possibility of a fuel leak. A fuel leak is a critical failure that must be handled carefully to minimize lost fuel. If the crew does not suspect a leak, then crossfeed can be used to restore fuel balance. However, if any doubt exists about whether there might be a fuel leak, do not open the crossfeed valve. Serious incidents have been made much worse in the past by opening the crossfeed valve at an incorrect time. A separate checklist exists for a fuel leak that again asks the crew to evaluate the possibility, and if a fuel leak is suspected in the right tank, to turn off the APU in case the APU feed line is the source of the leak. The checklists do not provide additional guidance, however crews must consider diversion and be prepared for an engine flameout when fuel supply in a tank is exhausted. If it is uncertain if fuel will be sufficient to land with the engine running on the leaking side, preemptively shutting down the engine in flight may be the safer course of action rather than having an engine failure on short final or even during the flare. The final abnormal for the fuel system is the fuel 1 or 2 low-level warning. If this message triggers, the corresponding AC pump should be turned on to ensure multiple pumps are trying to supply fuel to the engine. Excessive maneuvers and pitch attitudes could cause fuel to slosh away from the pumps and lead to a drop in fuel flow and an engine flameout. When a fuel low-level warning triggers, the aircraft should be landed as soon as possible before these engine flameouts could occur. We will now answer some review questions regarding the material covered in this presentation. Try to answer the question before the answer is displayed. Pause the video if necessary to give you the time to answer the question. Let's begin.